Welcome, friends, to Science Talk. I am your host and resident oceanographer, Jim Massa.
Well, good evening, my friends and Jim's friends. Welcome to Environmental Coffeehouse as always. It is great to be here on a Sunday night. Sorry about yesterday. I was under the weather, even though the weather was glorious. I was under it. And here we are. And I am not on anywhere. We are only on YouTube tonight. I am not multi-streaming. I'm not doing any of it. YouTube is it. I forgot to share on Blue Sky. I hope that's not a problem. But hey, Jim, we have a packed show. Why don't you tell everybody what it's all about and say hi? And Kim, thanks for moderating so far. You're the moderator here, and Looney's here. Hi, Looney Tunes. Thank you for moderating. Everybody, thanks for being with us.
Well, good evening, everyone. Thanks for joining. Hi, Kim. Back at you. Well, let's see what we're going to talk about tonight. Is AMOC slowing? That's the main topic, and then towards the end we'll look at see what the current conditions are for ENSO, what the where it's at right now. Now, with respect to the AMOC, I recently did a quick little video on my channel that did a gloss over kind of like the main points of this paper, and then I posted a deep dive video to my paying supporters on Patreon, Buy Me a Coffee, and my YouTube community. It's a 90-minute video.
Yeah, I know. I watched it.
And it's a really interesting paper. It's just published a couple of months ago, and what's interesting about it is that they looked at heat fluxes to rebuild AMOC in the past and where it's currently going now and so forth. So it's a new approach. One I think makes totally logical sense, and so I just thought it would be kind of interesting to talk about that tonight. Okay. Kind of hit upon what I thought were the major figures that help sum up the essence of their research.
Cool.
So we prepared a little PowerPoint slide show. So I guess we can.
All right, let me pull up the screen share, and we will get going with this. This is great. It's very nice, actually. I'm really happy with it, and I'm happy that you did it. As long as it's good and everybody can see it, let's go. And he's doing the heavy lifting tonight, folks.
So, basically, as the title of the my first slide is AMOC slowing, and I know Sandy will include it in her show notes,
Oh, yeah.
but down below is the URL to the research paper where most of these figures come from, and so and that was the research paper I based my long video on. So if we can hit the next slide.
Yep.
So don't know if it's visible, but I thought it would be a good
Right
idea to
here.
just include the
Wait a minute. Something happened. Hang on 1 second. Something changed. I don't know why. Give me a second to fix this. I don't know why it's going like this. What did I say, Jim, about this stupid software I got? It's supposed to be right here. And I can't see our screen and I don't know what's happening, but we'll do the best we can. Go for it. I
okay.
don't know why we
I
can't see us. Can we see us? I can't. Oh, god damn it. Hang on. Hang on.
okay, well,
Yeah,
I'm not sure
it's
why. Not sure why
no,
it's bouncing around
I
on you.
don't know either. That's why. I think I'm going to close it and start it again. Hang on. Hang on. Hang on. Hang on. Let me end the slideshow. Let's get us back and figure out what I did wrong. All right, let's go for it. I think we're good now. I'm not touching anything. It's not the right software, put it that way. All right, let's go.
So I thought it'd be important to go through the abstract to kind of sum up their findings. And what they're basically saying is AMOC is crucial for global ocean carbon and heat uptake. It also helps control the climate around the North Atlantic. Despite its importance, quantifying AMOC's past changes and assessing its vulnerability to climate change remains highly uncertain.
Mm.
I think this leads to a lot of, question: is it slowing? Is it collapsing? You hear all sorts of hysterics, basically. Like with aerosols and sea surface temperatures and so on. Understanding uh, past AMOC changes has relied on proxies, most notably sea surface temperature anomalies over the subpolar North Atlantic. Okay, how many times have you heard me say that at high latitudes, sea surface temperature is not a good way to assess things? Oceanographic.
At high
It does
latitudes.
at
Right.
high latitude.
Mm-hmm.
Salinity determines the density,
Mm-hmm.
which means changes in salinity. Yeah, there's going to be some changes in temperature, ocean temperature, you know, but changes in salinity is what really drives density currents at high latitude. Low latitudes, the tropics, yeah, it's going to be temperatures. So, you keep that in mind. So when you see that, when understand that it's salinity and not temperature at high latitude, of course, sea surface temperature is not going to be useful at high latitudes to get a handle on the AMOC. So
Ah.
what they said was that we use 24 Earth system models (ESMs) from the CMI PC, the coupled model intercomparison project phase 6. Now we're up to phase 6 to demonstrate that this is an important sentence. These temperature anomalies cannot robustly reconstruct the AMOC.
Hmm.
Translation: it's useless.
Oh, well, okay. If you say so.
Instead, and this is the important bit, we
Mm-hmm.
find that air sea heat flux. Now, I put in parentheses, this is what I put in parentheses here, from ocean to atmosphere, where ocean atmosphere highlighted. That's my insertion to clarify that we're talking about heat flux going from the ocean to the atmosphere and not necessarily the other way, atmosphere to ocean. So when we look, so when they said that when we look at the heat flux from the ocean to the atmosphere, anomalies north of any given latitude in the North Atlantic between 26.5 degrees north and 50 degrees north are tightly linked to the AMOC anomaly at that latitude on decadal and centennial timescales.
Make sure everybody knows the difference.
The decadal is 10 years, right?
10 years,
You know,
right?
and centennial is 100 years.
Okay, that's all. Just to make sure if there's any newbies out there, you got it.
So basically, what they're saying is that how heat moves from the ocean to the atmosphere,
Yeah.
which then drives currents, is what will drive AMOC. On
Okay.
these timescales, air sea heat flux anomalies are strongly linked to AMOC driven northward heat flux anomalies through the conservation of energy. On annual timescales, however, air sea heat flux anomalies are mostly altered by atmospheric variability and less by AMOC anomalies.
Ooh, that's
So
important.
it,
That one.
it is very important
Mm-hmm.
because what that's saying is that people trying to go, oh, it's the AMOC is doing it, whatever. It must be the air temperatures now. It's just too much variability, and it does not explain well what AMOC has done over the long haul,
Right.
the long time period.
Right.
Based on the here identified relationship in observation based estimates of the past air sea heat flux in the North Atlantic from what they call reanalysis products, the decadal average AMOC at 26.5 north has not weakened from 1963 to 2017, although substantial variability exists at all latitudes. Now the question comes, what's the business with 26.5 degrees north latitude?
Mm.
Well, as we'll see in a couple of slides here,
Mm-hmm.
that basically equates to the very southern tip of continental Florida,
Oh, yes.
26.5 north.
That's what I saw in your
So,
video. Yep.
so what basically when AMOC is flowing, the atmospheric temperature gradient is
Mm-hmm.
moderate. It's and the sea surface temperature gradient is moderate. When AMOC is not flowing, we have very strong, sharp gradient where the northern latitudes get really cool and the lower latitudes get really, really warm. So basically, what they're saying is that, and we'll see this later, is that when there is high heat flux at lower latitudes, that means AMOC is not necessarily going to be flowing northward.
That's interesting.
But now keep in mind,
Mm-hmm.
okay, you're still going to have the Gulf Stream. You're still going to have the North Atlantic gyra.
Sure.
It's that what happens at 26.5 north is going to impact what the North Atlantic drift does.
Mm-hmm.
North Atlantic drift is the current that comes off of the Gulf Stream as it swings over on the North Atlantic current. I know it's confusing. You have the North Atlantic current, which is part of the gyra. You have the North Atlantic drift,
Mm-hmm.
which pinches off the gyra and goes up to Scandinavia, Greenland, Iceland, up that way.
Okay.
So what happens if you have a lot of heat flux at lower latitudes, eventually it's going to translate in that the North Atlantic drift ain't going to be moving about.
And therefore lies the issue.
And therefore that slows down, so
Yeah.
you're not going to get the sink, because AMOC is what? Atlantic Meridional Overturn
Overturning.
Circulation. That
Mm-hmm.
means it's sinking. And if the North Atlantic drift slows down, you ain't going to get the sinking.
Mm-hmm.
You know,
So it's not
remember,
weakened between 63 and 17, although the substantial variability exists at all latitudes. And a lot of people want to, well, you say, be hysterical. Oh, but it's not.
You know,
And we've said
you know,
this. How many shows have we talked about this? I mean, we have many.
and just a reminder, it's like, as you know, Earth is a liquid planet, and as long as it rotates,
Mm-hmm.
you're going to have gyres,
Yeah,
which means the
that's
Gulf
true.
Stream ain't going away.
Right. Right.
Because first of all, you have an atmosphere for the moment, right?
Mm-hmm.
We have an
Mm-hmm.
atmosphere. There is solar heating that creates temperature difference. Then you create a wind stress. You get air that blows across the water. That's called a wind stress. And what happens with gyres is that the wind stress imparts a movement on the water. It creates what's called pressure gradients. Water moves down the pressure gradient, and so in order to balance the rotation of the planet, the Coriolis parameter, as well as the pressure gradient, as well as the wind stress and the wind stress curl, as well as any vorticity, which vorticity just means tendency to rotate, all these
Yes.
things have to be balanced. And when you balance them, you get a gyre in the ocean.
Okay.
So the Gulf Stream ain't going anywhere. What we have to
No.
look at is the North Atlantic drift. That's the issue.
Okay. That's the issue.
So so now if we can look at the next slide, slide number 3.
Without everything going haywire. Wow, this is a wild one.
So what this is the AMOC anomaly in Ceardrops. Now the anomaly, what they did was you notice the time period 1850 to 2016.
Yeah.
So what they did was they were able through proxy data recreate uh, you know, what the sinking rates were basically. And so that would be the average,
Oh.
and then the anomaly is the deviations from those sinking rates.
Okay.
So, you know, so in other words, if it's positive, then it sank at a greater rate than the average. If it's negative, it sank at a slower rate than the average.
Okay.
So negative is less sinking, positive is more sinking. And when you look at this, and throughout all their graphics here, green represents annual averages, orange represents decadal averages, and blue is the overall or centennial averages, or the whole shooting match from 1850 to
It,
2016,
it, it does look
2016.
like that. It does. What a
And
mess.
yes, it looks like a big buckshot.
It
And so those are all so they
does.
plotted the anomaly against the the sea surface temperature anomalies. That right? The horizontal scale
Oh,
is sea surface
yeah.
temperature anomalies.
Yeah. Look at that.
And yeah, they've put in some fitted regression lines. You can
Mm-hmm.
see the blue, the orange, and right, and the green.
Yep.
And they gave the shading represents the error or the range, plus or minus one standard deviation.
Mm-hmm.
And you can see and if you look at the R square values, so for the annual averages, the R square is 0.15. It's zero point 0.3 for decadal and 0.12 for overall centennial. In other words, it's shit.
In other words, it's shit. Okay. Okay.
In other words, when they said that sea surface temperature does not robustly, when it's crap, there it is. It's right there in this graphic.
That's pretty cool, Jim.
They
It's a,
show it
yeah.
right there. The
Yeah.
sea surface temperature anomalies has nothing to do with what AMOC is doing.
Wow. All right, good. That's good to know. It's good to learn. It's good to remember because when people do talk to you about AMOC and they say, oh, this is happening, you can at least have that little bit of information. You can say, well, the sea surface temperatures, AMOC, no, sorry. See Jim's videos, right? Yes.
So again, to repeat, as a question and a comment. On the vertical scale, we have the AMOC anomaly. In other words, does it sink at a higher or lower rate than the average
Mm-hmm.
versus the subpolar gyre sea surface temperature anomaly? In other words, negative values is below the average, positive values above the average for the time period indicated at the top of the graph.
Yep. Then we had some other things down there, but that was just pieces that made up this graph.
That that's them projecting out
Right.
into out 2100.
Oh, here it is.
Which
Yeah, 2100, right. I didn't look
you
at
know,
this earlier.
and and basically, the R square is for the three time periods under consideration does improve, but um, you know what they're
But we
basically
don't
still
know.
saying is that sea surface temperature really does not is not going to help.
Right. And it's a model. Yeah.
Tell us, yeah, and it's, yeah.
Okay.
So slide number 4 is a schematic to kind of give you an idea of what they're looking at here.
Love this
And
one.
if you look at the horizontal black line, you can see how it basically lines up with the tip of southern Florida, the
Mm-hmm.
continental Florida, not the Keys or anything like that. And it says here the schematic representation of the North Atlantic heat budget. So heat transport into the region from the south, indicated by the big, wide red arrows, can be compensated by number one is heat transport out of the region to the north, and that's if you look at the very top, you'll see like three green arrows,
Mm-hmm.
going up to Iceland, east and western sides of Greenland, past Scandinavia.
Mm-hmm.
Okay, so it's heat transport out of the region, basically, what the North Atlantic drift would be doing. Two, heat loss to the atmosphere. Those are the blue squiggly lines that you see. And three, a change in ocean heat content indicated by the overall orange shading.
And that is changing. I mean, we all know that.
That is changing. Now, what happens is that as we're AMOC to slow down, then you're going to see the orange at the higher latitudes uh, becoming paler, shall we say, and you'll see it becoming brighter. I don't know how to describe it in color terms, but you will see a sharper temperature gradient because of indicating more heat fluxing taking place at lower latitude than being, say, distributed somewhat evenly over the course of, you know 30, 40 degrees of latitude.
Okay, so in layman's term, let's say you were saying this to somebody that knows absolutely nothing. Uh, in layman's terms, then the heat and the heat content. What is this going to mean
Well,
for the future?
we have ocean heat content, and if it's not going to be sinking or
Right.
moving horizontally, it's going to go
Right.
vertically upwards. So
Okay.
if the North Atlantic drift slows down or totally stops, then more of that heat's going to stay at lower latitudes, and you're
Ah,
going to have a higher rate of heat flux to the atmosphere at lower latitude than at higher latitudes.
okay. Gotcha. And what's the
Whereas
scenario?
if the North Atlantic drift is tooting along, then you're going to have a more even distribution of the heat fluxing.
And that's the typical historical way it's been.
Well, for human civilization,
Right, for human civilization. But we're talking the potential for a lot different behavior.
potential for a lot different behavior,
Yeah.
which, thanks to the work of Wally Broker, has shown that this has happened before in the past. As far as the cold blob off Greenland, that's due to all of the ice melting and pouring into the
Sure.
ocean there.
Yeah, it
So
is.
this gives you an idea of what they're trying to address here in the research.
Okay. Good. Good. That's good to know. All right. We
So
moving
now,
along?
yep, number 5. I like this one here. So again, on the vertical axis, we had the AMOC anomaly in sphere drips, right? Again, that's a negative value means that the sinking was less than the average.
Mm-hmm.
Positive is more than the average.
Mm-hmm.
And we have the North Atlantic air sea heat flux anomaly. Notice the units: 10 to the 21 joules per year. 10
Okay.
to the 21 is
That's
what unit?
is what? Jeez.
What's 10 to the 21?
A
Your
lot.
favorite word? Your
Fuck.
favorite word?
My
It's a
favorite word.
zettajoule.
Oh, Senator. That's a Senator. I told you, Jim, that you were doing the heavy lifting. I have no brain and I hadn't studied today. Usually, when I do these shows with Jim, everybody, I study for 2 days and I relearn all the concepts, but I did not do that. I told him, doing the heavy lifting. So if it seems like it's going over my head tonight, it might be.
Well, you, you know, we can't do a podcast without me mentioning zettajoule at least
Zetajoules.
once.
Oh, that's I'm gonna get that tattooed on my arm. Zetajoules with a big drip or something. Okay. Rishi says, "Wake up, Sandra." Zeta baby.
So basically, they're
Yeah.
plotting the AMOC anomaly against the air-sea heat flux anomaly. Same thing.
Okay.
Green is annual, orange is decadal, blue
Mm-hmm.
is the whole time period in question. And as
The
you can
over.
see, if you look at the green, it's all over the place. It's a
Yeah.
buckshot. It's a buckshot. You notice that the error is a lot wider,
Oh, look at
a
that.
lot wider. It's a wide error there, because of a high, standard deviation is very high, so you got a wider one plus or minus one standard deviation. But if you look at the orange, you see how the
Yeah.
dots are pretty much in a
Staying
linear,
around the
and then
decay. Yeah. Yeah.
and the same thing for the overall, the blue.
Staying around the
And if you
decadal averages. Look at that.
And if
Huh.
you look, you see the fitted lines
Mm-hmm.
through there. The orange and the blue are almost like the same uh, equation, and the plus or minus the width of plus or minus one standard deviation for both of those is very very narrow, which means it's less error. And then you can tell that by look at the R square values. R square for the annual is 0.22, not good.
Why?
But
Why?
because of what they
Explain.
said earlier, too much atmospheric variability.
Ah, you have to give us the little, the little bit of extra. So it's the atmospheric variability that's going to
which and we which we
problem.
and we know that the atmosphere varies far more greatly than does the ocean due to the specific heat uh, value of water being much much higher than for air. So, and plus there's wind and so forth and so on. So the atmosphere, and when they say that the atmosphere, too much atmospheric variability in determining what AMOC does is not useful. We see it right here. We saw it in the earlier graphic that sea surface temperature of annual basis is not a good indicator for what happens with
Okay.
AMOC, because
All right.
AMOC is a long-term
Yeah, it
uh,
is.
thing.
It is. That's right.
Now take a look at the R square for zero
Oh,
point
sorry.
0.7 for the decadal 0.74. That's pretty damn good.
And why is that? Why is that pretty damn good?
Anytime you get an R square of in excess of zero point 0.7 for
Mm-hmm.
and one variable
Mm-hmm.
uh, has that value, that's showing that one parameter is explaining a lot of what is seen, explaining a lot of the variability that is observed.
Okay.
Take a look at the overall for the entire time period.
Right.
R square of 0.95. That's
Yeah.
almost like every data point is on the line exactly.
Yeah, look at it. You're right.
I mean, that's
Look at
that's
that.
pretty that's excellent.
Hmm.
That's
Hmm.
really excellent. So what is so what but now what is this telling us? This is telling us that when the air sea heat flux anomaly is positive, the AMOC anomaly is negative. So when you get a lot of
Oh,
heat fluxing at the lower latitude, AMOC at the higher latitudes is going to slow,
all right. That's what it. Okay.
and and vice versa. They're inversely related. No, we calculate an R square, right? You calculate an R square, which shows you how well the data fits the fitted line. You can also calculate another parameter called R. R is a correlation of the coefficient of correlation, which tells us how well the two variables are related to each other. And the values of R go between -1 and 1. R squared is between 0 and 1. And no, you do not
Yeah.
calculate R by taking the square root of R squared. You do, it's another, because otherwise you can't take, otherwise you won't get negative values. But so if I were to calculate an R value for the decadal and the overall average, I
Right.
would expect to get values very close to -1.
And why is that? Why would you expect that?
Because the very high R square values and -1 show they're inversely related.
Okay.
You
And
increase one, the other decreases.
right. And that's what we're
A
talking
positive,
about with what
and
could
that's what we're
happen
talking about.
in but what could happen in reality. Yes.
And if they were, you know, positively correlated, then when one increases, so does the other. When one decreases, so
Right.
does the other. Here, when one increases, the other decreases.
Right.
When one decreases, the other increases. And that's what we're seeing here. So when the heat flux anomaly is high or is above average, the sinking is lower. And when the heat flux anomaly is below average, the sinking is higher.
Okay.
Let me
And
say
then
that again.
yeah, say it
When,
again.
when the heat flux anomaly is positive,
Mhm.
the sinking of AMOC at the high latitudes is lower.
All right.
When the heat flux anomaly is below average, the sinking at high latitude is higher.
Gotcha. And then down here they've got more of the going
More,
projecting the
yeah,
future.
more projection. Yeah.
Mhm.
So
Their
so
models.
this shows it very nicely that what heat flux is doing at lower latitude can impact what's happening at higher latitudes.
All right, that's very cool. So we now know this. We
We now know
probably
this.
did, but I mean, it's now I could explain it. Okay, I
But
like it.
but this is like the first research I've seen of looking at heat flux. Seriously.
Oh, really? It
Yeah,
is.
really.
Oh my
Looking at
gosh.
heat flux directly relating it to and that's what caught my attention. Let's go, ooh, this is new.
Oh, that's why you wanted to do this because you said, and it makes sense because I don't remember us discussing this specifically. I don't. All right. All right.
Okay, common. Basically cold water sinks, hot water floats. That works great in freshwater systems, careful in oceanic systems, because you could have very warm, very salty water that will sink below cold,
Whose
not as
comment was
salty
that?
water.
I just pulled them up.
Uh, Moon
Lightning.
Man 75?
Oh, Rishi. Okay. Okay. Basically, cold water sinks, hot water floats. All right. So go over that
And
again.
you could have very warm, very salty water that
Mm-hmm.
will sink, be more dense than colder,
Right.
cooler water that's not as salty.
Yeah.
You have to be really careful with that, and
Okay.
that's what drives a lot of oceanography is trying to figure out the TS curves, the temperature salinity curve. An example of what I just said is the Mediterranean, right? Mediterranean water goes out Gibraltar. Yeah, it's very warm water. It's also very salty water. It's like 37 parts per thousand. And what does it do? It sinks down to about 700, 1,000 meters, right below the surface waters of the Atlantic.
That's so wild.
And that's why when it goes and becomes a North Atlantic intermediate water, and then it goes, Coriolis aims it right for Fram and into the Arctic Ocean.
Cool. I got it. I got it. Yeah. All right. We moving
The
on?
next slide is, yep, next slide is
Yeah.
pretty wild.
Oop. It did it again, this big stupid thing. I can't, I gotta get it back. I don't know why it does that. Are we good now? Yes. It all of a sudden it goes gigantic and it goes onto my other screen and it really screws me up. All right. We're here.
So now here I'm going to look at the one on the left, A, because that ties in direct. Well, it actually is a
That's
buildup
heat
on the
transport.
prior slide.
All right.
But what we're looking at now is we're looking at the actual meridional heat transport anomaly. We're actually now looking at the movement northward.
All right.
The ones with the AMOC anomaly was looking at basically sinking. Here we're now looking at movement of water from lower latitudes to higher latitudes. So, and we still have on at the bottom here with the air sea heat flux anomaly. We still have that. We're still doing, green is annual, orange decadal, blue is the whole thing.
Yep.
And we see the same thing. The annual is not a good predictor. Wide, big, plus or minus one standard
Mm,
deviation with there. So there's more error involved, a higher standard deviation. We see more basically a buckshot. We see the R squared value is not good, 0.19. Okay. But when we get to the decadal and the 1850 to 2016 average, we have very tight plus minus one standard deviation, shading. And we
okay.
see, that we look at the R square, 0.71 for decadal, 0.93 for the entire time period. In other words, what this is saying, and this ties into what I just said about AMOC sinking at high latitudes, when the air sea heat flux is positive over the anomaly is positive, meaning more than the average,
Mm-hmm.
the movement north
Okay. Okay.
is decreased.
All right. Repeat that. Just repeat that again.
When the air sea heat flux
Uh huh.
is greater than the average, that's what the anomaly means, the
Yep.
deviation from the average.
Right.
When it's greater than the average, the movement of water north is less, right?
Okay.
See how it's positive here and it's negative on the
Yes.
vertical axis,
Yes.
and vice versa. When the
Oh.
heat flux anomaly is less than the average, the movement north is greater than the average. To get more water moving north, because as the water, if you have a lot of heat fluxing,
Mm-hmm.
the water's not going to be moving. But when you don't have the heat fluxing, the water's going to be moving, and it's driven by basically physics. It's driven by temperature changes. It's driven by gradient changes. It's driven by conservation of heat.
Yes. So let me ask you a question about the heat transport anomaly, and so the decadal averages are not at all good to try to determine what could possibly happen through the air sea
Oh,
heat
no, 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 no,
flux.
no. Decadal averages are quite a good
They're
indicator. We
better
have
than the annual. Is that what you? Oh yes, yes,
much.
yes, yes. Much
Look,
better.
look, look,
I got it
look at the R.
backwards. Yeah.
Yeah, look at the R square value. You
Yep.
have R square of 0.19 for annual, but
Yeah.
it's 0.71 for decadal.
Yeah. I got it
So
backwards.
decadal is a better indicator, and then the whole 1850 to
Yep.
2016 is
Yep.
is even a better indicator.
Okay. That's what I got it mixed up backwards. This is good. I'm understanding, which I love.
And then on the right side,
Yeah.
okay, this is really cool. We're back to the vertical axis having the AMOC anomaly,
Right.
right?
Mm-hmm.
And then we are plotting that against the meridional heat transport.
All
So
right.
it's not the air sea heat flux. Again, the same
Oh.
thing. The annual, decadal, and the whole time
Mm-hmm.
period in line, and we now see a positive correlation. And actually, it's really interesting. This is where, excuse me, this is where the annual actually
Oops.
performs best,
Mm-hmm.
because we see a 0.84 for the annual R square, 0.94 for decadal, and 0.98 for the entire time period.
Which is a
So
big one.
we,
Yeah.
we yeah, we would get high R values of close to +1. But what this is telling us is that, and not surprising, if you move more water northwards, you're going to have more sinking northwards. And if you move less water northward, you're going to have less sinking northward. That's what this tells us.
Jeez. All right. I'm going to put your questions. We'll be answering them. We still have some more stuff, but I see a cue, so I'm gonna mark it off. Thank you, Gary. Okay.
So this, these two panels here in the prior one there, to me, are the crux of this paper.
These two panels? These two panels, really?
Those
Oh.
two panels and the one before, to me, are the crux of the paper.
All right. And you explained why, which is the best part.
So this shows us directly that one, heat flux impacts what happens, with the system, and then two, and then this one here, if you increase the heat transport, you're gonna help increase the sinking, right? Because if you have more water sinking, you got a conservation of volume. You have to move more water into the area. If there's less sinking, you don't move as much water into the area. So then you're sinking. So then the movement northwards slows down. Directly related.
Directly. Wow. Pretty cool. Gotcha.
So then they in their abstract, they went and stated that AMOC has not changed significantly over the past 60 years or so.
That was
And
it.
now,
Hmm.
well, hang on. So now the question becomes, what constitutes a significant change in AMOC? This has to be. It's not
Great
defined.
question.
It needs to, because here AMOC is collapsing, AMOC is slowing, it's doing this, it's significant. What constitutes, one, a slowdown, two, a significant slowdown, and what's meant by collapse? Does collapse mean total stoppage?
Yeah.
Well, I think we know what. I think we will know when that happens. We'll actually be able to. Oh, there's no more sinking at all.
We'll be
Okay,
dead.
we have a stoppage.
Hmm.
Okay, we have a stoppage. So they didn't put it in the paper. So what the graph that you're showing up there
Hmm.
is one I created.
This one.
I went into
Okay.
the yeah, I went into the data, and I took all the AMOC values that they reported. They
Over the
have
60 years. Yeah.
yeah, they have like a supplemental thingy in the paper. So I went and
Okay.
took that and I
All
plotted
right.
it. And I plotted it. I fitted a linear regression line through it,
This one.
and
Yep.
yeah, right. You can see the little dotted line right
Yep.
through here.
Yep.
And then I put a little panel in here showing the equation. And hang on, I got to kind of tear into this a bit. The equation is y equals, I'm just going to say
Zero.
1.85,
Okay.
1.85 times 10 to the negative 3x minus basically 3.6. I'm just doing some rounding.
Okay, guys.
Okay.
You got that because it's going to be on the test.
Okay. That's not the important thing. Okay. There's your fit equation. The important thing is the p-value. You see the p-value of 0.12. What is that p-value referring to? That p-value is testing the coefficient for x. In other words, is the coefficient for x that gives you the slope of the line, right? Remember from basic high school algebra,
Oh,
y equals
God.
mx plus b, right?
Yeah,
Right?
100 years
Remember
ago.
that?
Yeah, barely.
Right? Where m
Yeah.
was the slope, b is the y-intercept.
Yes,
Okay,
yes, yes.
so the slope here is that 1 point, times 10 to the minus 3. That right?
Yep.
That's your slope.
Yep.
Okay, so the p-value here is testing, is this slope, is this coefficient for x, which represents the slope, does that significantly differ from 0? And when you get a p-value of 0.12, and if you're testing at the 95% level, then
Mm-hmm.
the critical value is 0.05. If you're testing at the 99 level, then the critical value is 0.01. In other words, a value less than either zero point zero 0.05 or less than 0.01 would tell you have a significant result. Well, 0.12 is greater than either of those values, which means we have an insignificant result, which means that, in essence, this line does not differ from zero.
This line.
This fitted line, the little dot dash
Yeah,
line there,
it doesn't
does
differ
not
from zero, even though it
does not.
does look like.
Yeah, I can change the scaling on that, and that thing will be flatter than a board.
I got ya. Nope. Now I understand the anomalous. Okay, and these points are the 60 years of
Yeah, those points
measurements.
are the 6 year. So
Yeah. Of
basically,
the.
when you test for the significance
Yep.
of the coefficient, what
Mm-hmm.
the null hypothesis is that the slope of the line does not differ from zero. The alternate hypothesis is that it does. Here in this case here, we have to accept the null hypothesis
Mm-hmm.
that the slope is not significantly different from zero, which means you have a flat horizontal line. That's what
And
this
that
tells us.
and it tells us really then what the paper was all about. The 60 years, it has not significantly changed.
It has not and that's what they're saying.
And these are
And
variability points. The anomalies are just where
yeah,
it
and if you look at the R square value, the R square value is really not great. It's like 0.05 or something like that. So the R square, which means it's kind of all over the place.
I see.
So
Well, 60 years of all over the place. However, Jim, let me ask you a question then. 60 years of all over the place. Pre 1960, was anybody measuring this, or would it have to be retroactive in time models?
well,
I mean, did
well,
anybody know how to do this? Were scientists hip to this?
what are they doing? They said they looked at proxy data. They went back to
Prox.
1850. So
That
they
was in
took
the other
proxy
one.
data.
Okay.
That's what this whole paper is based on, proxy data.
Okay. All right. It's all proxy data because I know
And
here, but
whatever they have measurements for, plus plus using proxy data
okay.
to
Okay.
reconstruct what happened in the past. But that's that's what they
Gotcha.
stated. They used proxy data plus
All
this here,
proxy data.
and whenever we do climatology,
Mm-hmm.
we're using proxy data.
Right.
When we say, if what's happened in the Younger Dryas, what's happened in this, we're always using proxy data to reconstruct past climate situations.
Exactly. That's the cool part I find. You know, the reconstruction and then using the models and using the history and it's really cool.
So,
Tells us a lot.
so, so, so when they say that we state that AMOC has not slowed significantly, they're basing it on this here,
Yes.
and their their data is correct. I wanted to show that, but however, if you look at this carefully, especially starting from around 1975-ish or so,
All right.
it almost looks like there's a wee bit of a sawtooth pattern there.
This right here.
The actual points themselves, it looks, it reaches
Yeah, look at that.
a high value, then it comes down, it goes back up, it comes back down, it goes back up, wiggles a bit, goes back up, comes back down.
What would
It
explain
almost
that?
well, hang on.
Yeah.
It almost looks like this is cyclical. Well,
Oh.
we need to be very careful because, yeah, you may look like cyclical, but and we have techniques to determine signals and cycle
Mm-hmm.
in time series data.
All
We
right.
can use we can use the Fourier transform, we can use the Fourier smoothing function, and so we can do that and then pick out any signals. And that's a common technique. For
Mm-hmm.
those who may remember their calculus studies, you probably were familiar with power series, where you explain functions through a series of exponential of excuse me of power function, like x to the something power, and a whole bunch of other x terms to a something
Yep.
power, like a Taylor or Maclaurin series. Fourier series are trigonometric series, and especially for sine and cosine, which tend to be cyclical. So, the cautionary note here: while this may look cyclical, do not jump the gun, because the
But
last
it's
data point I
not.
have here is
Right.
you never know. Hang on. You, let me go with my thought here. Because it goes up, it comes down, it goes up,
Yeah.
it comes down, it goes up, it comes down. Oh, that
Ooh.
sounds like a cycle. But
Yeah, you're
okay,
right.
what happens at the very last data point here? Does this continue downwards, or will it go back up? We don't know. If it does go back up, then an argument might be made where maybe this whole thing is cyclical. We don't know. We would have to apply the analytical techniques to do that. So, as a caution to, not to being to avoid the temptation of saying something cyclical, let's jump down to slide number 9 first. Then we'll come back to 8. Okay. You look at this here, and you kind of say, well, that almost looks like a nice cycle. 1 hertz or something
Yeah.
like that.
Go
It
up
almost
and
looks like
down.
almost like a sine curve. Well, in this case, it'd be negative sine if it were, right? It'd be tempting to say we have something cyclical going on here. Go to the next slide, number 10.
Oh,
That that number 9 slide issue, the one I just showed you,
yeah.
is part of this overall function.
Okay. That's what I
In
thought.
other words, I cropped it at x equals -1 to x equals +1. And really what this is this function is f of x equals x cubed minus x. It's not cyclical at all. It's not cyclical. We just have some interesting things going on here where we end up what's called a relative maximum and a relative minimum. But in this function here, as x goes to positive infinity, the function goes to positive infinity. X goes to negative infinity, so does the function.
So
So
there
this is
really,
why I say
yeah.
it's that's why I say you have to be cautious and not be
Right.
tempted to say something cyclical. You
Right. And
you
that
need more
would
data, and then you need to apply techniques to analyze it
it
to
would
look for those
connotate
signals.
people saying, okay, it's cyclical. We don't have to do much more work. This is the way it is. This is not the way it is. No, there's always more analysis involved. Did you want to go
So now if we
back?
can we'll go back to slide 7, please. Okay. So now you have heard me say, whether on this podcast or in my video, that AMOC is slowing. We've been measuring the slowdown for the last 20 years or so, right? And if you look at the tail end of this graph here, it would, except for this one little burp
Little
upwards,
the
it
burp.
it would look like it's slowing down. Right,
Right.
we've been right. Teams from Dalhousie and Halifax, Dartmouth, Nova Scotia, the Norwegian research, we've all been measuring the slowdown. Anyway, it's slowing down. So what I did, and now this is slide number 8. What I did was I took these last data points here, and I ran a regression on those data points. And when you look at the regression
Oh,
just on that, okay, now take a look. We have
yeah.
the equation is y equals minus, because it's negative slope,
Mm-hmm.
0.0672
Mm-hmm.
x plus 135.4. But now look at the p-value, 0.00005. In other words, the slope does significantly differ from 0. We have something going on
Oh,
here.
that's pretty wild. Look at that. So you're looking at
And
the overall 60 years, and then you get close and you're looking at just the last several years or this chunk, and you see a difference.
you see, and the R square is much better. It's 0.88.
Hmm. That's interesting, Jim. I see.
So now the question is, well, Does this mean AMOC is significantly slowing? Well, if we accept that a significant slope is answers that yes, then yes, it is significantly slowing down.
From this
For,
analysis.
over the last 20 years.
Right. So, what does that mean for everybody to understand?
We need more data because for all we know, no, seriously, for all we know, this thing could turn around and go right back up,
And what would
or
happen?
a
Why would that happen?
whole bunch of reasons.
Not just, you
Atmos-
can't just answer and say,
Atmosphere,
yeah,
heat content, all the parameters we keep looking at.
okay, everything. So, any one of them could cause
Yeah,
a change.
or it could keep going down, 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 down.
And well, where would we be?
Yeah, well, I'll be long pushing up the daisies by then.
Yeah,
But
but
but so that's why so with every new year of data that they get, they're going to need to upgrade the overall
okay,
regression that they did.
question, who's they and who's funding it and what's happening? I mean, we're going to the last one, right? So
Who's
before
they?
we, yeah, who's
Just,
they now?
just the researchers here. Go to the paper. Go to the
Yeah,
link that that I provide. Here.
Columbia,
That's
NOAA.
yeah. Well, Sandy will put it in the show note. But
Right, but are they
just go to the.
losing funding? I mean, what if this work that Columbia and I mean, we're in a different state.
Because of
Who
the
will
orange
do the
asshole.
work? Who will do the work once the
Yeah.
United States drops off the radar? Who's going to do
Well,
the work?
that's a political question. I don't want to get into that now because I'll get really pissed off.
All right. I just had that thought because there's a lot of work here. There's a lot of research, and I
Yeah.
know other
This
countries are
yeah
gearing up.
this this work needs to be continued. But with the current political situation here, it's
Who?
probably in
Right.
danger of not being continued.
Or continued somewhere else, and maybe Canada and, or another country that's interested that this is critical work, I think. I mean,
Well,
listen,
look at the folks at Dalhousie University.
okay.
They've been looking at AMOC for 20, 30, 40 years.
All right. Yeah,
So
it will go
but
somewhere.
this is one of these things that we actually need more data to ascertain what the hell is happening.
I'm just hoping that we can actually have the scientists, even if it's not in the United States, that we can continue all of these amazing projects because they are. They're not short of amazing, in my opinion, anyway. I
Look,
mean, today, Jim, I read that the Department of Energy is actually striking three words climate change from anything and emissions, believe it or not. So it's so me asking this question on who is going to continue this research is not really out of the bounds, and I don't want to get you angry, so we'll go and now we will move on to the publications.
yeah,
So,
because this this work here is vitally important. I actually think this is an excellent piece of research.
yeah.
Yeah, I offer my critiques in my long
Which is
video,
great. Yeah.
which centers on this last graphic. That looking at that the linear regression
Mhm.
for the last 20 years or so that
Mhm.
shows that the decline is significant. So that was a critique I offered in my long video analysis. But overall, this is excellent research. This is like
I'm
amazing
glad.
research.
I love that you're excited over it, and that's why it's very important because if you really like it, then I trust that this is something that absolutely needs funding and continues. So this was just a report we're not going to go over, but it is new and it's actually from the NOAA. And so recent evolution, current status, and predictions. We're not going to go over it really, but Jim, did you want to just give a little so people in the audience that might want it, it'll be in the show notes. You can check this out.
It'll be in show notes. It's like 79 pages long. So
Right.
yeah,
It's a big thing. If anybody wants to
it,
find anything that's read the summary, you know? Read the summary and you'll understand why he included this just to show you.
and they go through incredible detail here as to with the data and so on. And I guess basically you may want to download it because
Yeah.
who knows how much longer it will be up on the public domain
Right.
available.
I think it looks great. I mean, the U.S. seasonal precip and temperature outlooks. I mean, to me, this is something I would want to have. So I will download this. I did not, but I'm going to download it because this seems to me like it makes sense as something I should read and familiarize myself with for our future shows. Okay.
I mean, right now, the summary, the very first sentence, ENSO neutral is present. So that's the first thing they say.
Mm.
So, but
Yeah. And they say it's updated once a month, second Thursday of the month, in association with ENSO diagnostics discussion, which you can find. And hopefully, like Jim says, we can find it. This is in the Climate Prediction Center. Unfortunately, we're in such a, in a very, we don't know. We really don't know. We don't know what happens, what's going to happen when the big, beautiful bill kicks in. So let's hope. Download
yeah,
everything, guys.
yeah, and they're waiting for after the midterms, like yeah,
Right.
because they know how badly it screws people over.
Oh,
So
this looks great.
the the index or the index the website. I'm looking to see where. Okay, there we go.
This one?
Yeah, let's look at no. Let's look at the SOI index. Yeah, the next one, the other one. We look at
Oh,
that SOI. So no, the
wait
other
a
one.
minute. Where
Go
did it go? Ah, shit.
what's the first tab over there?
This one.
That
This is
one.
it. Oh, the
That,
first one. Dumb me. Sorry.
that
Forgive
tab.
me. I'm not a good producer tonight. All right. Here we go.
So we're going to look at three tabs of this page here. Again, this is a decent website.
All right.
And the first one is the Southern Oscillation Index. And the SOI is a standardized index based on observed sea level pressure, SLP, differences between Tahiti and Darwin, Australia. The SOI is one measure, just one measure of the large scale fluctuation in air pressure occurring between the western and eastern tropical Pacific, i.e., the state of the Southern Oscillation,
Mm-hmm.
during El Nino and La Nina episodes. In general, smooth time series. Okay, smooth time series. What I just mentioned earlier that some of the techniques we use in analyzing time series data is the Fourier smoothing.
Fourier
Tech,
smoothing. Mm-hmm.
that's what they're referring to here because it
All
looks
right.
for cyclical
Mm-hmm.
stuff here. Uh, so 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 where was I? Smooth time series of the SOI correspond very well with changes in ocean temperatures across the eastern tropical Pacific. The negative phase of the SOI represents below normal air pressure at Tahiti, above normal air pressure at Darwin. Okay, prolonged periods of negative, and I'll go
Mm-hmm.
back and read for the positive, but prolonged periods of negative SOI values coincide with abnormally warm ocean waters across the eastern tropical Pacific, typical of El Nino episodes.
All right.
Okay, so if you have positive phase, that means you then have above normal air pressure at Tahiti and below normal air pressure at Darwin. So prolonged periods of positive SOI values coincide with abnormally cold ocean waters across the eastern tropical Pacific, typical of La Nina episodes.
Okay.
Now, what's really cool about this graph that was presented here is
Mm-hmm.
you can actually put your cursor over here and you can scroll along and it will give you a calculated value for the SOI by year,
And
and
then,
sometimes several per year. So basically, if you see negative values, you're
yep.
in an El Nino situation.
Yeah.
If you see positive values, you're in a La Nina situation. And when you go all the way over to the very, very, very far right,
Yes.
with the latest data I
La
have for
Nina.
August 2025, you
Mm-hmm.
have zero point 0.4. Now, SOI values between negative zero point 0.5 and positive zero point 0.5 indicates neutral state. Neither La Nina, neither El Nino.
Yeah, and how often
So,
has that happened here?
well, scroll along.
Yeah,
You
not.
can
Yeah.
you can see it.
Yeah.
Just scroll along.
Look at that. Oh, yeah.
Usually,
This
to
is
go from one
cool.
to the other, you have to transition through the neutral.
Oh,
Usually,
but they're not all doing. No, every year did not do that.
that's it.
No.
Usually.
Yeah, usually. Look
But,
at that.
but right now we're at zero point 0.4, which is the neutral state. Now the indications could be, and we'll look at this in the next when we pull up the next URL. We're not done with this URL, but
Hmm.
the indications are that we're probably heading into a mild La Nina, not necessarily a strong one.
Okay, so what does it
But
mean? Tell everybody. Refresh their memories.
well, the La Nina, the ENSO cycles affects temperatures and precipitation patterns.
Yep. Yep.
Usually for Alaska, La Nina means a cold winter.
And La
Yeah.
Nina is less, uh, if I'm not, El Nino produces maybe more, is it more frequent storms, more, hurricanes in an El Nino year?
It depends on which ocean basin you're
Yeah,
looking at,
that's true.
with the teleconnections and so on. Um, but what, yeah, the other thing is, like, typically a La Nina, I think, means the more drought region for the for the southwest of the U.S.
And we're not
For
even in the Southwest and we're droughted
But
in the
but
East.
also don't
So,
forget
yeah.
that when you look at the ocean temperatures, the coldest La Ninas of recent years is still warmer than the warmest El Ninos of 40 years ago, 30, 40 years ago.
Lightning Rod says less heat from the oceans and more transport of cold, low salinity to the northeast of Greenland. Less heat from the oceans and more transport of
Well,
cold,
well,
low.
you're transporting warm water up north. You're
In
introducing
yeah,
cold water from the Greenland ice melt,
right,
but you're
right, right.
transporting warm water from the north. Now, the ice melt will dilute the salinity,
Yes.
you know, because everyone knows about SST, right? Sea
Mm-hmm.
surface temperature.
Yep.
We also have SSS, right? Sea surface salinity. We
Salinity.
also measure that,
Yep.
but you don't see that often being reported. But we do measure that.
And why wouldn't they report on salinity? What's the problem with telling people about salinity?
Well, you see it in the academic papers and the peer review papers.
Right. But not. It's just sea surface temperature is it's the headline
It's the headline. I
because
mean,
everybody
you
knows.
have journalists who are not necessarily scientifically literate
Right.
trying to write story, and then the editors want a headline,
Yeah.
that whole stuff.
Sure. Right. But that's why we
And,
are more familiar with sea surface temperatures. Hmm.
and if you try to start talking about salt, say, "What are you talking about? What's salinity? What is salinity?" Then you have to explain what salinity is, and they go, but people
Well
just get
then, Jim,
confused
you
over
have
that.
to teach a entry level sea surface temperature, sea surface salinity course.
So anyway, so speaking of sea surface temperature, might as well click on the SST tab.
Okay, let's go to the SST. Here we are. We're at the SST now. Equatorial Pacific Sea Surface Temperatures. SST.
Yeah, they describe what ENSO is, and they break it down into several regions of Nino 4 3.43 and Nino 1 plus 2, and the regions are indicated in those little boxes that you see in the graphics there.
Yep.
And historically, scientists have classified the intensity of ENSO based on SST anomalies. You know, so that's what
Sure.
they do there. And then in addition to the southern, excuse me, in addition to the Southern Oscillation Index, we have the Oceanic Nino Index and ONI, the ONI, and warm phases are defined as minimum of 5 consecutive 3-month running averages of SST anomalies in the Nino 3.4 region, surpassing a threshold of plus minus 0.5 C.
Okay, so here's the ONI index. What is it used for?
It's used to tell you what's going on with the oceans.
Okay, so but in 3 month blocks, and would forecasters use this in their forecasting of what might be happening in a given region?
They would figure it into their overall modeling.
Okay.
Now, when they say 5 consecutive 3-month running averages, think of
Yes.
it like this:
Yeah.
January, February, March,
Sure.
February, March, April,
Mm-hmm.
March, April, May,
Right.
April, May, June, that kind of stuff.
Okay.
And you can do the same thing. Excuse me. Ugh, crappy weather today out on the crap. But you can do the same thing here. You can scroll over the ONI graphic, and it'll give you it'll
Yeah.
tell you
Let's
the
see
three
what it looks
months.
like.
Like for example, I just randomly fell on 1966, and I have DJF 1.4C. you
And
know,
I'm
it,
falling on the old age. Okay, great. All right.
so you can scroll across,
Look at
and
this.
if you go
Ooh.
say to
Ooh.
JAS.
Black. What was the black? The MJJ. Where is it? Where's the MJJ besides marijuana? See?
Well, MJJ would be what, May, June, July.
All right, so we had black. Mostly it's been in the upper or lower. Black means what is black? On the line. Just no change, no warm and cold. Neither one. I want to find it
I don't,
again.
I don't see a
Oh,
black line.
see here,
I'm
black.
seeing,
See, black in
I'm seeing blue.
1970. 00.0. I mean, it was zero. In, um,
1970.
yeah, pretty wild. I mean, these are different, from the norm of what you would expect. There's been years where there's been
Oh wow.
not
Okay,
zero. Yeah.
yours is showing black. On my page here,
Oh,
I'm actually getting blue and red when I
okay.
scroll across.
Okay, well we've got blue and red, but when it hits when like back in 1970 when it was zero at the line, 0C line, it's black because it's zero. It's nothing. Zero. The measurement
Because
is
there's no
literally. Go ahead.
well, it's the anomaly. There was no
Yeah.
deviation from the anomaly. In other words,
No.
it was the exactly the average value.
Right, exactly. So it happened. That's pretty cool. Thank you for that explanation. I really liked it because now it makes the graph makes this a little bit more relatable.
And if you go towards to the far right side here, I'm
2003.
like I'm on October, November, December of 23, and I have 1.9 C in the red. So really warm conditions. And you might
Okay.
recall we
Oh.
had a pretty strong recent El Nino a couple
Oh.
years back.
Yeah, we did a show. I'm sure I could look it up. Yeah, look at that.
You know,
It is. It is. It what? Ooh, it got warmer. Definitely. Look how high this goes. Holy shit.
and then June,
Yeah.
July, August of 24, I get a zero point
Mm.
0.0, right? So I get a
Huh.
black right
So it goes
on
back.
June, July, August 24.
Hmm.
And but now if you look at in the of late 24 to the data of this year, we're a little in the blue.
Mm-hmm.
So, and of course, it's going to be a lag effect because of the
Cold
3 month
phase.
running
All right.
average.
A
But
little cold
this is
phase.
this is also another way to see what's happening with the ocean temperatures as well, the sea surface
Yeah,
temperatures. And so it's a good way to gauge what's happening. That so you can use this here and tie it in to the index, the SOI index itself.
that's cool.
So
Yep.
then we can look at the OLR, which is the outgoing long wave radiation.
Ooh.
This is what atmospheric scientists like to always base everything on.
Right, because the heat goes out. Right, right, right. It's not holding it in, but it is holding it in. Yeah.
So the outgoing long wave radiation, because remember, energy comes in the UV
Yep.
part of the spectrum and it goes out in the infrared part of the spectrum. So the OLR at the top of the atmosphere are observed from advanced, very high resolution radiometer, AVHRR,
All right.
instrument aboard the NOAA Polar Orbiting Spacecraft.
And it's up there now. The NOAA
For,
Polar Orbiting Spacecraft is up there.
and if I recall correctly, these satellites typically are meridional, so they orbit by going over the poles, not like following
Oh,
latitudinal lines. So they
okay,
follow
gotcha.
longitudinal lines.
Cool.
Because sometimes in the
Wow.
wintertime, I'll look out at the sky there, and I see a little blinking light moving across the sky. I go, oh,
Oh,
that's one of those satellites.
yeah, because you're up there on the pole. Yeah, that's cool. Very cool. All right, so
So,
let's talk about this.
so data is centered across the equatorial areas from 160 degrees east to 160 degrees west longitude. Raw data converted into standardized anomaly index. Notice calculate an average, and anything that's above the average is positive, below the average is negative. Negative OLR are indicative of enhanced convection and
Yeah.
hence more cloud coverage typical of
Yep.
El Nino.
I think this would
Okay.
be an interesting the on outgoing long wave radiation for aeronautics aviation. This seems like something that would be important with with their weather, with their standard weather reports. This could
Well,
give
I
you
guess that's
yeah.
something you can pose to Nicholas.
I love aviation. I don't like flying. I just like studying it and watching it.
No, no, no. You
Oh,
talk
oh,
about the atmosphere because that's something that's
absolutely.
Nicholas's
Absolutely.
wheelhouse.
Yeah, it is. It is. This isn't his, but this is cool.
So basically the red. So the red, the
Yep.
negative oil are
Yeah.
indicative of enhanced convection. Therefore, there is more cloud coverage that is typical of El Nino. So more convective activity in the central and eastern equatorial Pacific implies higher and therefore colder cloud tops, which emit much less
Oh.
infrared radiation into space.
And it all stays and makes a warm ocean. Mm,
Now,
mm, mm.
reading the blue, the positive. So
Mm-hmm.
positive OLR are indicative of suppressed convection and less cloud coverage, typical of La Nina episodes. Less convective activity in the central and eastern equatorial Pacific implies lower and thus warmer cloud tops, which emit more infrared radiation into space. In other words, less heat trapping ability than with when you have a higher, colder cloud tops. So the clouds are higher up in the atmosphere, and therefore they'll be colder on the top of it. The bottom is a different story.
So is La Nina a preferable? type of weather pattern to people than El Nino?
Given all the global warming that's going on, yeah.
Okay, I thought so.
But 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 you have to think about what it does to precipitation patterns and so on
Sure,
and so forth. It's not just
wreaking
simply, oh,
it's
what's the air temperature doing?
right, but it is wreaking havoc. It
It,
is.
because when we had that strong El Nino a couple of years back, back in 23, yeah, the sea surface temperature going crazy, and things were getting hot, and there was all sorts of crazy weather patterns going on
Mm,
because there was a lot more heat flux to the atmosphere, causing more precipitation. It was a bonkers.
yes,
A couple of years back,
pretty
we saw
wild.
all the flooding all across the planet.
Yep.
So, of
It's still happening, Jim. It's still happening in
course it
so
is.
many places all over the planet. Just go to Volcaholic. But you're not on X, but I do follow her because she collates everything that's happening, and it is insane. It is.
So you can, but again, you'll see a lot of the atmospheric folks. They look at the TOA, the top of the atmosphere. What's the heat coming in? What's the heat going out? They
Right.
then use that to calculate the Earth energy imbalance, and that's an incomplete picture.
But this completes it.
No,
The
well, this is
some
just
of it.
tied into it. They're looking at
Ah,
UV in, IR out. They're looking at strictly the top of the atmosphere, the top of the clouds. They're not looking at under the clouds, the lower atmosphere.
sounds like a
You know, they're not
song.
they're not looking at the heat flux from the ocean, which contribute to the Earth energy imbalance. Because if you have all that ocean heat content in the first place, that's because of all the Earth energy imbalance in the first place from
Right.
burning the fossil fuels.
And that is what you always hit home.
I'm
Is
always
that
railing
it's
against
right.
that.
It's the ocean, stupid. Yeah, that's I know that. And you do. You make your point and you do make a good point. So where are we going?
So anyway, so folks who are interested in, you can pull up these URLs and just explore these graphics. It's really interesting. ENSO forecast. That's where we're on next.
Yep. Here we are. And what
And
pray tell us the ENSO forecast, Jim?
this was published September 19th. So this
All
is
right.
like basically,
Brand new.
9 days ago.
Yeah.
And it's a monthly summary of the status of ENSO based on the Nino 3.4 index, that little box that we looked at earlier.
Yep.
As of mid-September 2025, Equatorial Pacific remains in an ENSO neutral state, with sea surface temperatures in the Nino 3.4 region close to average, but exhibiting a gradual cooling trend.
All right. All right.
The IRI ENSO plume forecast indicates a moderate probability, 56%, of La Nina conditions developing during September through
Okay.
November
Good.
2025. These La Nina conditions are expected to persist through the boreal winter of 25-26, December through February.
Mm-hmm.
However, beginning in January through March, so there's going to be a little overlapping, ENSO neutral conditions are forecast to return, with probabilities ranging from 55 to 74%, while the likelihood of La Nina gradually decreases. The chances of El Nino development remain very low, below 10% through March to May of 2026. And the graphics below are showing those probabilities.
So this
So
to me
the
sounds like it could be a positive, wouldn't it
so the
be?
summation is that overall we're probably going to be in an ENSO neutral
Yeah.
state with some La Nina tendencies, unlikelihood of El Nino developing. And so basically for the next 6 months, expect neutral to very mild La Nina situations.
Okay.
That's basically the take home from that.
All right, folks, you understand? It's La Nina. It's La Nina. Okay, can we do the environmental coffee house flush of the day? We'll flush El Nino. Bye bye. Why not? Why not flush El Nino? We like La Nina better today. All right, Jim, where do you want to go next?
Well, that's all we've got. I
All
guess we
right.
can
So
we
with
can
the
open up the question.
okay, okay, let me get us back to the regular screen. Regular screen. Now, everyone, remember you have homework. You have homework. We're going to test you. I'm going to have the test available. All right. I know I'm being silly, but that was a lot of information. I liked your graphics. I have to go actually go over them again. Well, your presentation, is that something that I can put a link to, that actual presentation, or is it something that I have to email to somebody that wants it? Or is
What
it
presentation? What presentation?
the one that you just did, the first one,
Oh,
the
tonight?
presentation? Yeah, that you put together. Yeah.
Oh,
Is that a shareable? Like,
it's not linkable as far as like a
okay.
URL or anything because I just
All
threw
right.
together a PowerPoint.
Okay. Well, if anybody would want it, you can email me at environmentalcoffeehouse.com.
How if you're interested, if you're a paying supporter of mine, I do have the 90-minute video of that paper on my Patreon, on my Buy Me a Coffee and YouTube
Okay.
community.
It
So
plays on Buy
it's
Me a
there.
Coffee? The video plays on Buy Me a Coffee.
Well, I did a link to Patreon.
Oh, okay. Because I was like, I'm on Buy Me a Coffee. I've never been able to do that. I've been waiting for
Yeah,
them to do it.
I keep asking them, it's like, when are you be
Well,
able to let us directly upload
yeah.
vids?
I'm on Substack, but it's free, but I'm enjoying the platform. And I think I'm going to be using it more because I like writing. And so, yeah, you should check it out. If you're on Substack, aren't you?
I think
Well, I'm starting to use it. I liked it. I sent out a scathing one today.
I think I have an account there, but I have not been able to figure out how I can be a creator on there.
Oh, all right. Well, maybe I can help you with that. But I do like it. I have not used it for videos making live streams yet. A lot of people do. It's I have to figure out the RTMP. I think it's just the setup. And Ecamm Live, which is my software, does not have it automatically programmed like they do everything else. Every time you do a Substack live, even if you do it on YouTube or whatever you do stream it, you have to set it up every single time. It's not just a click. So it's something I have to think about. Recently, I haven't wanted to think. Okay, what oceans rising at Obama builds oceanfront in Hawaii and a waterfront home in Martha's Vineyard? Hello. Well, sure, because they have the money and they have the attitude of it isn't going to happen, because a lot of people have that. Oh, it's not going to happen to me. It's not going to happen to me. No matter if East Coaster, if you are wealthy or not, people naturally feel, even if they are educated, they just feel like it's not going to happen to me. That's a normal thing. It's a normal thing. It's almost a defense mechanism, you know? Okay, let's see. Questions. I had one. No super chats, but questions. Um, Gary, so what could cause the shutdown of the North Atlantic conveyor? Here we have another half an hour. So what can cause the shutdown of the Northern Atlantic?
Well, I did a recently a 4 video series discussing that. Basically, recent studies are showing that even with all the melt coming off of Greenland, that and there's a lot of water coming off Greenland, but because it's pouring in at volumes relatively less than major events of the past, that the water, that fresh water gets entrained and mixed, so that yes, the sea surface salinity is decreasing and could slow down the sinking, but as far as what can actually shut it down, completely stop it in its tracks, you have a whole pile, basically the entire ice sheet of Greenland just falls into the ocean, melts at once in situ. Seriously.
Yeah.
But the more that the ice melts back,
Yeah.
the less likely that where you're going to have a lot of icebergs all at once in the ocean. about 13,000 years ago, you had Lake Agassiz, and Lake Agassiz was basically in the middle of the Canadian Shield. It just suddenly let loose. You had all this fresh water that went gushing into the North Atlantic, and it shut down AMOC. Right now,
Damn. Say
what
what
concerns
happened? Yeah.
what concerns me now is the freshwater buildup in the Beaufort Gyre in the Arctic Ocean. Because if you get conditions just right, you can take that freshwater accumulation, which is the result of river runoff, increased precipitation, melting sea ice, right? You get this buildup and enough of it, and you get the Arctic dipole conditions to line up just ever so perfectly. You can suddenly have a big flush into the North Atlantic, and
A
then you
big
shut down AMOC.
flush. Did someone say flush? Another flush. Two tonight. We have to bring a little levity into the show, Yeah.
So that's another mechanism that basically a huge, like, inland freshwater sea
Hmm.
suddenly goes into the North Atlantic.
Yeah, that's
A
catastrophic.
major input of icebergs
Yeah.
that all melt in situ at once.
Yeah. That's not going to happen. Tain't going to
That's not going to,
happen. No.
but all this meltwater is impacting AMOC. It is slowing down, as I showed
Right.
in the slideshow.
Ever so
the
slightly.
the slope was significantly different from zero, and it's negative, so that would seem to say that AMOC is significantly slowing down currently.
Hmm.
At what point does it become problematic? I.e., at what point does it stop totally? We don't know. But we're already seeing the impacts of the slowdown of the last 10, 20 years, because the folks in Scandinavia, the UK, Iceland, they're kind of getting cooler conditions already.
Oh, yeah. No kidding. We have to follow up on
As
that.
I said before, that a slowdown in AMOC in the past, well, when it shut down in the past, we had hemispheric cooling.
Hmm.
I don't think that's going to happen because of all the ocean heat content worldwide. But what I think will happen is with the slowing down of AMOC, you're going to get regional cooling. And we're starting to see the signs of that now.
Not here. We have regional drought and it's not cool yet. Downstairs in my basement, it is. My poor kittens are freezing to death down there. What a difference between temperature downstairs and upstairs. I mean, I have my own little scientific experiment in this house I live in. It's like 20-degree difference sometimes. All right, let's see, guys. Well, Graham. Hi, Graham. I noticed the UK summer was hot but wasn't off the chart. That's always nice to hear, though. It is nice to hear that something wasn't off the chart. I see who is here? Who stopped in? We have a comedian in the audience, too. uh, I really don't think we have too many questions, Jim. I could go all the way back. I think people have to, some of the stuff has to be digested to understand it. You're very, you're teaching us a course. That's basically
Well,
what it is.
there definitely was a lot of info in there.
Yeah.
Uh,
But still, it all leads to the one place. The research was great. You explained the research, and then you explained your take at the end and showed us the the smaller amount of time that actually shows that yes, AMOC is being affected. So over the 60 years, it may not seem like it's dramatic, but when you look at a closer lens, it is, and it could stick, right? It could
yeah.
stick. There would be a reason it could stick. We don't know. That's the whole thing. So I put it in layman's terms. It could stick, but we don't know. But you're
Yeah.
showing that the potential is there by drilling down into a smaller time period, which I thought was pretty very cool. It's fascinating. So thank you. Thank you very much. All right. Well, I think I don't know. I think we're almost near the end. We've been an hour and a half. I think that for me tonight, that is very good. We don't have a lot of questions, which I'm kind of surprised, but that's
Ac-
okay. Yes,
Actually,
sir.
I see one from Graham. Has sea levels started to rise on the east coast of America? Yes,
All right,
we
I
are
didn't.
seeing
Oh,
sea
here it
level.
is. Yep.
We are seeing sea level rise on the east coast of America, and that and we're seeing a higher rate of rise. In fact, it's accelerating because of the physics. You have what's called Western intensification. You have the meltwater from Greenland. The physics helps
Oof.
push that water towards the east coast or the Western Atlantic. So yes, we are seeing uh, a sea level rise on the eastern
Okay.
seaboard,
All
and it
right.
is a bit.
Well, then, I guess the Obamas might be a little screwed if it happens any faster than previously expected. Up there on Martha's Vineyard. How's that one, East Coaster? Oh, this person. I think this person's a troll, but it's okay. You're a funny one. How long have I been driving a broom? Honey, I rode a Harley for 36 years. I can outdo anything you have to throw. But anyway, it's kind of funny to have a troll here. It's not usual here. Jiffy. Freezing, melting point of water ice increases or decreases with salinity. Why?
Okay, we have what's called freezing point depression, meaning that the more salt or more solutes, let's put it that way, the more solutes you add to water, the lower the freezing point becomes, and that has to do with the way the ions of the solutes intersperse with the water molecule. So it takes more energy to be removed to separate them out from the water molecule. So therefore, you have to lower the temperature to to affect that, where you basically get brine rejection, and then the water can freeze. So we have freezing point depression. The more solutes added, the lower the temperature is that to freeze the water. In the Arctic Ocean, it's about minus 1.8 C. Okay, is where seawater freezes. And then on the flip side of it, you have boiling point elevation, so that the temperature which the water boils is increased because, again, the interference of the solutes with the water molecules. So it takes more energy
Good.
to bang them apart and separate them.
All right. Well, there you go. I think that I hope you're happy, Jeffrey. I think that was pretty good. And we had a lot of fun in the chat I saw, and I banned the asshole because he insulted Looney Tunes. And if you insult my mods, you're right the fuck out of here. So, bye bye. We don't get that very often, Jim. Seriously. Really, we don't. All right, wait, we have one more. Scott, the increased meltwater weight is causing increased volcanic and earthquake activity. Do you agree? Ooh, that's another show, Scott. That's
I can't really
interest.
speak to that because I haven't seen any studies that directly look at that. I do know there have been some studies showing that uh, the increasing melting of ice caps and ice sheets is changing the distribution, the mass distribution around the
Mm-hmm.
planet, which is then causing changes in Earth's rotation rates. As far as what it does to tectonics and volcanism, I I really can't speak to that.
All right.
You need to look up papers on that. Um, I do know on land, for example, when ice sheets melt back, you get what's called isostatic rebounding. So does it work the other way? You add more weight there. You have a higher weight pushing on the plates. Can that cause something? Intuitively, it would make sense, but again, we would need to see direct research paper.
Okay. Very cool. All right. Well, I want to thank everybody for being here and not the trolls. We banned 2 people tonight. Holy shit. That's like a record for Environmental Coffee House. But you know what? Bring them on. I say bring them on, but don't insult my guest and don't insult my moderators because you'll be gone. You insult me? Hey, that's par for the course. I'm the host. All right. Well, listen, guys, peace out. We will see you Tuesday night. I'll be here Tuesday night with Scott from End of the World Party. And we actually are going to do a night that is more, I'd say, support. Talk about all this, talk about your feelings, talk about how to deal with what we're living through. And we're going to try to bring a lot of positivity to the chat and to everybody. You know, we need it. And Scott's a good guy. End of the world party. He was with the Three Domingos. No longer. He is now Scott tonight, Tuesday. And Jim, what do you have coming up?
Oh, I don't know. More video. Uh, we had snow this, over the last couple of days. So, yeah, winter's here. Um, just want to address one point again. Addition of salt solute to water lowers the freezing point, increases the boiling point.
Oh, you saw that
So
question. Yeah. What
I
about
saw
good
that
humor
comment.
yeah, comment. Teasing rather than insults. That's fine because that's fun. Good humored teasing is nothing. We're not thin skinned here. Our name is not Donald Trump. But insults are not good. So, all right. Good night, everybody. Good night, good night, good night.
Good
Peace
night, all.
out.
Thanks for hanging.
Ba da 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 da.